physics, and I hope it's a bit of an invitation of the two communities or the topics you're working on and connections to the field of quantum information. And well, I'm in Copenhagen in the math department, and maybe you know my colleagues Bert van der Doorhoes and Jan Philip Soloway that I'm working very closely together with. But anyway, so I will tell you about a specific topic, namely entanglement, recoupling, and entropy, which I think has some very direct connections to your work, and highlight maybe a few others. You see an object in the background. It's a particular moment polytope that I'll talk about later. No, it doesn't work. Now it works. Okay, of course it's very nice here in Diableré, and you see some pictures of our family outing today on the cross-country slopes. My family is sitting over there, so they'll just watch for the beginning of the talk, and maybe we'll have a bit of a performance in a minute. I have another, very slow somehow.
To the ceiling.
Where do I have to point it?
The white thing.
The white thing over there.
Ah. All right. Okay. Here we go. That was our break. Next, there's several reasons why I'm here, and I think one of the reasons is that next year I will check out the place. Next year, maybe. It's not working.
Yes, it's.
Next year, I will be organizing a workshop on quantum information together with Renato Renner from ETH Zurich. And it's really sort of like on quantum information. And you're of course welcome if you're interested in joining, maybe get in touch with me, and then we can talk about it. The place is very nice, and you know that already, I guess. All right, so I came a little late. I'm sorry. I really have trouble with it. So I came a little late, and at the beginning of the week I was in Ghent at the yearly theoretical quantum information meeting. And it has grown. It grows at a rate of about 20% per year. It's now reached almost 1,000 participants. So 300 participants in each of the 3 parallel sessions. This year is the picture of the planning session in the morning. I just want to give you an impression, so I couldn't really miss it. It was this year in Europe. It's rotating on the different continents every year. So that's why I was a bit late. So apologies for that. But it's really an interesting event where mathematics, physics, and computer science come together in this endeavor to see what we can do with a quantum computer in the future. Right. I also want to tell you about my local environment in Copenhagen before I go to the mathematics. As I mentioned already, my colleagues Jan Philip Soloway and Bert van der Doorhoes. When I joined 9 years ago, the faculty there we established with money from the Willem Foundation. It's maybe you know the Velux windows, probably the windows here in the roof, the slanted roofs, are by a company called Velux, and the founder was called Willem Kahn Rasmussen. And so this Willem Foundation supports us annually with a contribution of 1 million euros, and so we've grown in size and hired 2 new faculty, so we're in total now 7, we're about 30 students and postdocs, so it's a very kind of active environment in theoretical quantum information. There's some other funding studies as well. So there's a lot of interest in quantum information, and I just wanted to let you know that of course, quantum information has this field where experimentally there is a big effort, and theoretically there's a big effort, and we theorists sometimes have the feeling that we get forgotten by the hardware developers, which really have a massive effort. So we're very happy that Margrethe Vestager, she's the Danish commissioner to the European Community, she's vice president of the European Commission, was visiting us actually, and we told her the message, and I think the message came very much across that quantum hardware needs quantum software, and so without new kind of quantum algorithms, if we don't develop them and if we don't develop this field, then we will actually don't know what to do with this fantastic quantum computer we're building. So it's very nice that I think she got the message, and now there's a lot of interest also from people that are on the more applied side. I don't really know how to conduct this talk, I have to tell you. So with there's also a pharmaceutical company that called Novo Nordisk. I'm not sure if you've heard of them, but they have 50% of the United States insulin market, and they have decided to now invest in quantum computing, and this is now a collaborative effort also with people building hardware, especially Eugene Polsik, that you might know. He builds a new atom array now in order to in the future then be able to simulate other quantum systems. Maybe we can, yeah, maybe it's the batteries, I don't know. Yeah, so this is maybe to preemptively kind of answer the question of, are you a mathematician or a physicist? And then usually the answer for me goes that I study physics. I'm a professor in the math department, but most of my grants are actually from computer science. So I'm really like a hybrid person, and it's very hard to locate us in this space. There is one piece of work I want to mention, because I asked a question yesterday at the end of one of the talks about the constructions of spin chains with certain properties, and the reason for that is that nowadays we have a lot of control, and we can actually construct certain objects with atoms, or also in condensed matter systems. And during my PhD, we have suggested one coupling, so where basically the couplings are in a very specific way engineered as to exhibit, so the couplings are not uniform, but they're but it's a finite chain and has certain properties, and we at the time, we came up with this type of coupling to enact sort of the transfer of information from one side to the other.
So it's still a nearest neighbor, just...
I will take my computer, I think. And then just without this, yeah, so I'll bring it in and take it off from there. I think it's better. Let's see if that works better. So. So maybe I'm sorry for that. Yes. So we had these things, and I think this is one of the areas where at least some of the work that was presented here could have a direct impact if one changes the mindset to engineer something. So rather than the mindset changing the mindset from the first quantum revolution of like observing the system and understanding it to manipulating the system, and this sort of change of mindset I think could lead to a lot of really interesting results. I have we've published this paper here, but almost 20 years ago. It still acquires one citation per week, so it's has far over 1,000 citations now. It's really interesting and has connections to integrability, special functions. I've worked also here with Luc Binet, who's started works in this field and is really from the community here, and but has also connections to graph theory. Graph theory is like Chris Gottshill from Waterloo, but very interested in this. And of course, more and sort of my community has direct connections to what we call the quantum walk, and that is also a number of things. So I think this is a touching point I will not mention during my scientific part, because what I want to talk about is recoupling coefficients, the 6J coefficients and their connections. But before, because I have I think quite a lot of time, so I want to actually give a bit of a background to this work and the connection to representation theory there. It's a paper with Peter Frana and Edwin Zaudam that just appeared. Yet now you see it's like 6 years, it's a long refereeing process, I guess, in mathematics in the Journal of the AMS. And then I come to a paper that was even earlier in the archive, but also took a long time to publish. That's this relation on recoupling theory. And if you have the slides later, you can click on them and find the papers. Yes. Entanglement. Entanglement is these quantum correlations, and it's a buzzword, but I think I sort of really what we want to understand is what the relation of the whole to the parts. And before I start now my scientific talk, I want to give a bit of an illustration of this. And you probably all know the cover of the Gödel-Escher-Bach book that really illustrates this concept that you have the whole and that the whole somehow connects to its parts, and in particular that the letters E, G, and B, you can immediately ask the question, which triples of letters can I reproduce with a wooden object? And one thing that I did, maybe 5 or 6 years ago was so my kids have the initials G, N, and E. So I built actually a wooden object that displays G, N, and B, N and E in such a way, and I think it's a fun game to think which triples can I represent and which can't I represent. And another thing I built actually while my smallest one was less than a year old, I built this wooden object that seems to project both on a square, on a circle, and a triangle. It's actually not completely true. The circle is not completely circular, but anyway, this is also really fun. I encourage you to think about these questions. And now I'll invite my son Niels, who will present to you one of these kind of whole to the parts that I have only recently just try to draw it for you. Okay. And it's a little bit of a different one. It's sort of like a two-dimensional one. Okay, I'll have to. When you start recognizing what it is, you're of course encouraged to shout out as loudly as you can. Das nächste Mal. Take the We had fun playing with these. Does anyone see anything yet?
I'm not quite sure I understand the rules.
Yeah, I'm not telling you because I thought someone maybe discovering the rules themselves. Tell you the rules, of course, in a minute, but. Okay, do you see it? So if you does anyone see? These are like 5 letters, right? So you can try to read them top down. What do you see when you read them top down? Georg, yes. So Georg, so that's the name of my oldest one. And if you turn your head sideways and you read it down like this. Yeah, and then you see Niels, which is the name of this one. But okay, thanks, Niels. Okay, so this. Thanks, Niels. Okay, I think we should clap for Niels. Okay. So, there's one you tried before. Okay, good. I think it's fun. I mean, you can now. I guess you have all these notebooks that you got from the conference. You can try and play. And the other day I was at the lab of my experimental colleague Charles Marcus, who maybe you know, he does kind of like these condensed matter things. And he said, well, Dr. Solfstetter was visiting, you know, a few years ago, and he, oh, it's the wrong way around. And he drew this one, which is really fun. And if you read it downwards, you see Bohr, and if you read it sideways, or if you put your head this way, it's like Niels Bohr. And here, if you put it sideways, you see Bohr, and if you bleed downwards, you see atom. That's really good. So this is no original Dr. Solfstetter, it's in the lab. Anyway, good, I'm coming to my sort of scientific part of the talk now, I guess. It was a bit of an introduction, I don't know how much time I have left. But, yeah, that's a good idea. So what's the philosophy in quantum information? Is philosophy really to view your quantum states as quantum versions of classical bit systems? So a classical bit system could be 0, 1, 0, 1, 0, 1. Of course you know all of that, but I want to put some notation. Or of course it could be up, 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 or any of the other 8 states. Whereas in a quantum system, where if I have 3 quantum bits, I have 0, 1, 0, 1, 0, 1, I can have superpositions, I can have linear combinations of them, and mathematically, of course, I introduce a basis of like 0, 1 and 1, 0 for a 2-dimensional space, and then I'm writing down, say, the basis vector E0 tends to E0 tends to E0 plus E1 tends to E1 tends to E1, and the question is kind of like, how do we understand the relation between the whole system, this 8-dimensional space, and the parts, right, in the 2-dimensional space. So mathematically, in a quantum system, of course, has a Hilbert space, and a Hilbert space is a complex vector space with the inner product. This is a completeness relation, etc., etc. But if we throw out the inner product, okay, we anyway work finite dimensional. So completeness is not an issue, but if once we throw